So CO2 is the greenhouse gas that we're most concerned about for climate change. But we're going to talk about methane first because it's easier and make it easier to understand CO2, which we'll do next. Methane is the second most powerful anthropogenic greenhouse gas, and so it's not negligible anyway. So methane is a transient gas. It's it comes out of a gas burner, and it can burn. So it's very high energy, and it actually burns in the atmosphere too, naturally, just under the influence of sunlight. The chemical reaction looks something like this. The methane encounters this guy who is called a hydroxyl radical. So remember in seawater, we had all these things that had charges, like the calcium that had 2+ and the carbonate ion that had 2-. Those are ions. Those can't really exist in the gases, but gases have these things which have no electrical charge, but they have extra electrons that are sort of hanging out there and very reactive. It's an unstable molecule, and it's written as a radical by putting this dot there. So the OH radical is formed from water losing a hydrogen, and it really wants to get that hydrogen back. So if it encounters a methane, it'll steal one of methane's hydrogens and leaving CH3 and the radical now on the carbon, and now the OH has satisfied itself and become a water. The average lifetime of methane in the atmosphere on average is 10 years. And that this reaction, the production, the availability of these radicals is entirely a function of sunlight. If it was dark, like in the bubbles of ice cores, it's very dark. And so you can measure the methane concentration from the atmosphere from 100,000 years ago, and it won't have reacted at all. So the atmosphere is like this very, very slowly burning candle flame, which is only kept going by the sunlight that creates these radical compounds. And actually, a candle flame works by the same sort of radical chemistry as this. So there are different ways that the concentration of methane in the atmosphere could be changed. You could either change how quickly you're releasing methane to the atmosphere, which we call the source of methane. Or you could change the amount of OH radical that is around for the methane to react with. So if we try the first case, if we start out where the reaction of methane is balancing its production here initially, but now suddenly we add a whole bunch of new methane to the atmosphere in an ongoing way, so increasing the rate of methane emission. At this point, you'd be putting more methane into the system than you're taking out, and so the methane concentration would rise, and the rate that methane will react will go up as you have more methane. And so then the reaction of methane will grow in until it balances the source again. And this takes about 10 years, that lifetime of methane in the atmosphere. Alternatively, if you did something that suddenly depleted the availability of this OH radical, you could start out with an equilibrium, and then suddenly the reaction rate would drop, and then the concentration would rise until the reaction rate again balanced the source. So this all should be looking a little bit familiar to you, because it's basically our old friend, the kitchen sink analogy again, applied to a totally different thing, where the source of methane is the water coming out of the faucet, and then the rate at which the water goes down the drain depends on the water level, the same way that the rate of methane reaction depends on the rate of on the amount of methane that's there. So if we assume that the amount of OH radical is staying the same, which it seems like it pretty much is, we can draw a equilibrium equation that says that the source should balance the reaction rate, or the reaction rate has to be balancing the source. It's a slave to the source in equilibrium. And that could be given by the concentration divided by this lifetime of 10 years. So the main way that humans are altering the methane concentration of the atmosphere is by adding new sources of methane to the atmosphere. So there are natural sources that existed before us and exist still today, and the main of these is swamps. So we talked before, when we were talking about coal formation, that when you have waterlogged soil, it's hard for oxygen to get down in there. And in that case, bacteria can produce methane from the organic carbon. And so you hear methane called swamp gas for this reason. If you step in a swamp, you'll see bubbles coming out, and then maybe the bubbles can catch fire in the atmosphere and look like UFOs. They blame UFOs on swamp gas, which is probably kind of silly. But swamps are a main source, a natural source of methane to the atmosphere. Termites and ruminant animals also produce methane in a natural way. Humans have impacted the story by growing rice, which we do in flooded fields. It's not that the rice requires the flooding, but it can tolerate it, and it makes it much easier to keep the other invasive plants out if the field is flooded. So a flooded field tends to make anaerobic conditions favorable to methane production. So rice agriculture is a major source of methane to the atmosphere every year. Our domestic ruminant animals, cows, also release methane. They exhale it, actually. It's not a bad thing. And then the fossil fuel industry is also responsible for some leakage of methane to the atmosphere. So looking at the concentrations of methane through time, it is about twice as high as the pre-anthropogenic value, which we can measure from bubbles in ice cores. And it was rising through the decades until about 1990, when it sort of seemed to reach this plateau and stop changing. Everything else about the human impact on the planet is growing. And so it's actually kind of a mystery why the methane concentration isn't going up. There are multiple theories, which is what always happens when you don't really know for sure. One possibility is that the Earth has been drier in the last few decades because of climate change. And so that cuts down the emission of methane from wetlands. Another possibility is that the collapse of the Eastern Bloc capped a lot of leaky methane to the atmosphere, but it's not really very well known. And then just in the last few years, there has been this uptick in the methane concentration, which is also not very well understood. So the future of atmospheric methane is sort of difficult to predict, given that we can't really tell you in detail why it has done what it has done in the recent past. However, the short lifetime of methane in the atmosphere means that if you want methane to go up, you have to keep adding more and more and more all the time. And if you cut back on the emissions, the concentration will fall within a fairly short time frame. So for atmospheric methane as a greenhouse gas, we got to recycle the kitchen sink analogy yet again. But for CO2, it's more complicated. So if we're going to use the kitchen sink analogy to understand what's going on, we gotta do some construction work here. So this is sort of what it would look like. The atmosphere would be a sink, and there'd be gas coming into it as before. But then there are these other sinks that are kind of connected to it by these tubes that run from one to the next, sort of sideways. So the fossil fuel carbon is a source to the atmosphere there, and it raises the water level in this atmosphere sink way up. And the first thing that will happen is that the water will run from this middle sink into those two other sinks. So I've drawn these other sinks as much bigger than the atmosphere sink because that's the way it is in the real world. What happens then is that the amount of carbon in the land reservoir maybe and in the ocean reservoir certainly will rise as a result of this fossil fuel carbon sort of spreading out to those other reservoirs. And then there is also the steady drip, drip, drip of water coming into this sink, which would represent the volcanic degassing of the Earth. And this is the consumption of CO2 back to the solid Earth by the weathering reaction. And so when all of these sinks have a water level which is raised up compared to what it used to be because we dumped a bunch of water into the center sink, they will eventually all settle back to the original equilibrium water level in a very long time. So there's different stages to the response to a CO2 addition here. First, it spreads out, and then the whole thing sort of relaxes back to an equilibrium. So if we look at the airborne fraction of a slug of carbon that's added to the atmosphere, it starts out at 0, and then we'll call this the fossil fuel era when the CO2 is rising. And at the peak, about half of the CO2 that had been emitted would be in the atmosphere. So that's where we are today, actually. If we were to stop emitting carbon dioxide to the atmosphere today, we would be right here with about half of the carbon we ever put in the atmosphere. Or if we stop in the year 2100 or whenever, it'll be about 50%, given how quickly we're adding the CO2. And then the recovery can sort of commence. There will be a fairly fast drawdown of the atmospheric CO2 on a time scale of centuries, governed by the 1,000-year circulation time scale of the ocean. And that will draw the CO2 down fairly far. It won't recover all the way to the original atmospheric CO2 concentration because this sink is bigger than that, but it's not infinitely bigger than that, and so the atmosphere still gets some. The next stage is when calcium carbonate dissolves to make carbonate ion, which essentially replenishes the carbonate ion stock in the ocean. So this is a neutralization stage. This is calcium carbonate is like Tums, and it's neutralizing the acid of the CO2. And when it does that, it replenishes the carbonate ion, which as the reaction partner of CO2, it's sort of like anti-CO2. When you replenish that carbonate ion, you allow the ocean to take up a little bit more CO2 because you're restoring the chemical buffer of the ocean. So this process takes a few thousand years, and it draws the CO2 down a little further, still not all the way to the initial value, but down to sort of 10% or something like that of the CO2. And then the last bit is this very, very long recovery due to the CO2 weathering thermostat, which, because the fluxes are so low, 0.1 gigatons per year is the weathering rate of igneous rocks, it will take a very long time for the ultimate recovery. So there's kind of a peak and a long tail to the CO2, as opposed to methane, which is just a simple single exponential decay. This is, mathematically, you would describe this as the sum of several exponential terms, if that makes any sense to you. If not, you can just look at the artwork. So there's the peak and there's the long tail. And there are a couple of factors which tend to de-emphasize the peak and emphasize the tail. And one of them is the band saturation effect, which is the fact that when you add CO2 to the air, the temperature response is not linear, but it kind of bends over like that. It actually, the temperature goes up as the logarithm of the CO2 rather than a direct multiplier times the CO2, which is what this shape looks like. So that means that the really high CO2 of the peak doesn't translate into as really high a temperature as you would think if it was just proportional. This function acts to sort of fatten up this tail relative to what it looks like just in the CO2 concentration. So looking at CO2, you say, oh, there's a big peak, and yeah, okay, kind of a long tail as a sort of afterthought. But when you look at the temperature, it doesn't have such a pronounced peak. It looks like the temperature just changes and pretty much sort of stays there. The other thing that tends to de-emphasize the peak is the slow ocean heat uptake time. To warm up the planet, you have to warm up the deep ocean. Today, as we'll learn in a future lecture, the oceans are keeping us cool because the excess heat from the greenhouse gases is slowly invading the ocean. And the time scale for heat invading the ocean is very similar to the time scale for CO2 invading the ocean because they're both controlled by the same circulation, about 1,000 years. And as a result, the temperature evolution from the peak over that sort of 1,000 years there is going to get chopped off by the slow ocean heat uptake. So that further makes, sort of de-emphasizes the peak relative to the long tail. Now, there are parts of the climate system that respond most strongly to the long tail because they take a long time to respond. And the poster child for that is really the ice sheets and their impact on sea level. So here is a plot of reconstructed changes in sea level due to changes in the size of the ice sheets from the geologic past. So present day, we are here, and sea level is by definition 0. And then this data point here is from the last glacial time, when it was maybe 5 or 6 degrees colder than today, and sea level was actually 120 meters lower than today. Looking further back in time, about 3 million years ago, was a time called the Pliocene, when there wasn't much of any ice in the northern hemisphere. And the temperature was somewhat warmer than today. It's not totally clear exactly how much higher sea level was then or how much warmer it was. It's hard to put together information from the past like this, but here's a best guess. And then further back in time, this is from a time when the Earth was in what's called a hothouse climate. So there was no ice at all on Earth. And the problem with understanding or figuring out the sea level during some time that's way in the distant past like that is if you find some fossil beach someplace, you don't really know if that's if that's at the same elevation today as it was then, because the land surface is moving up and down on geologic timescales. So this 70 meters of sea level rise at that warmer temperature is based on how much ice there is today. If we wanted to make a hothouse climate out of the Earth today with the continental geography as it is, it would raise sea level by 70 meters. So, there's a whole lot of complexity in this line, but there is also just sort of a fairly clear relationship, especially when you compare it with the forecast for the year 2100, which calls for some 2 to 4 or 5 degrees centigrade warming and a sea level change of maybe a meter or 2. So this is totally off of this line from the geologic reconstructions, and the reason why is because it takes a long time, longer than just from now to the year 2100, hopefully, to melt the major ice sheets. And so the forecast for year 2100 doesn't really capture the time scale of the problem of the ice sheets, and that's why this forecast is a little bit deceptive. I mean, it's useful because those of you watching this video probably not going to live beyond the year 2100 And so this is an anthropogenic, a human timescale, but it's not the timescale for the ice sheets. But if the CO2 is going to continue to affect climate for hundreds of thousands of years into the future, there's plenty of time for the ice sheets to respond fully. So this is an example of part of the climate system that is mostly sensitive to the long tail of the CO2. Other examples include carbon cycle feedbacks, warming the deep ocean and causing methane hydrate to decompose and release its carbon would happen on a very long time scale of thousands of years because it takes a long time for heat to get into the deep ocean. Or melting permafrost soils on land and decomposing the carbon that's frozen there will also take centuries, presumably, to happen. So these are all impacts that are much more strong to the long tail of the CO2 than to the actual peak itself.